Alrighty. So we'd calculated the resistance of a long wire of metal 3 based on a sheet resistance of 0.1 ohms per square. Now I'd like us to calculate the capacitance of our wire. And again, it's metal 3, so we can use these area capacitance values of 8 attofarads per micron squared for the area and 26 attofarads per micron squared for the fringe. And so what we should find is that the capacitance of our wire in total is going to be our area capacitance value, so 8 farads per micron squared times the total area, which is 3 times lambda for C5 process. Lambda is 300 times 10 to the 3 microns times 100 lambda, so 100 times 300 times 10 to the 3 microns, plus our fringe component, which is going to be 26 attofarads per micron squared, times the perimeter, which is going to be twice the short side, so 2 times 3 times 300 times 10 to the 3 microns, and then twice the long side, so plus 2 times 100 times 300 times 10 to the 3 microns. And get our calculators out. So I'm getting something, honestly, that doesn't make sense to me, so I need to recheck my numbers because it's looking like the capacitance is going to be 216 microfarads, which seems abnormally huge. So let me just make sure everything. Seems legit here. So 8 times 10 to the minus 18 times, let's see, 3 times 300 times 10 to the 3 is 9 times 10 to the 5. And then I have, so 9 times 10 to the 5 times 3 times 10 to the 7. It's 10 to the 12. I guess that actually does make sense as far as the units go. Sorry, let me write down my logic here, and then you guys can help me point out the mistake if there is one. So this is 8 times 10 to the minus 18 farads per micron squared up here. And then this guy right here, 3 times 300 is 900 times 10 to the 3 would be 9 times 10 to the 5 micron. And then this guy over here, 100 times 10 to the 3 is 10 to the 5. Another 100 makes it 10 to the 7. So this is 3 times 10 to the 7 micron. So 9 times 3 is 27 times 10 to the 12. Times 10 to the negative 18 times 27 times 10 to the positive 12. Yep, is 216. Microfarads. So, I don't know, the math is what it is. Anybody see any dumb mistake that I've made here real quick in calculating my surface area or anything? Oh, I see it. So 300 nanometers is not times 10 to the positive 3 microns, it's times 10 to the negative 3 microns, right? So that's going to make a huge difference. Yes. And that's going to change this guy as well. That makes way more sense. 21.6 attofarads for the area component. And 1.6 picofarads for the fringe. Yeah, so that's another thing that led me to believe that my answer was wrong, is I would expect the fringe capacitance to be much larger than the area capacitance for a long, skinny plate, which is what we have when we have a wire. So when I add these two things together, I get 1.628 femtofarads. So why is the capacitance of the wire important? Well, these wires have resistance and capacitance, so they're going to look like an RC network as well. We'll just treat it as a lumped parameter system really quick. So the delay time should be something around 0.35 R times C. 0.35 times our resistance of 3.333 ohms times 1.628 times 10 to the minus 15 gives us 1.899 times 10 to the minus 15 seconds. So that's on the order of femtoseconds. Does this make sense? Well, if we look at a quantity called the intrinsic delay, which is based effectively on the speed of light in a vacuum, we can see that this length, that we should get, let's see, 2/3.0 times 10 to the 8 meters per second times our length here of 300 lambda, or length of 100 lambda, excuse me. The intrinsic delay is 200 nanoseconds. So what does that mean that we got a delay of 1.9 femtoseconds earlier? Well, that's actually faster than the speed of light would allow a wave to propagate through this particular medium. The actual delay that we would see would be 200 nanoseconds. So the metal contribution to the RC delay is typically negligible, and it's largely due to the fact that the resistance of the metal layers is so small. All right, so let's see what I want to talk about next. Just a moment. All right, so let's talk about connecting metal layers to metal layers real quick. So let's say, what color have I been using for metal 2? Kind of a purple. So let's say that I have a section of metal 2, like so, and I'm going to connect to it a section of metal 3. So we have a place where metal 2 and metal 3 overlap, and that has to happen if we want to connect between the metal layers. And what we'll do is we will put in what are called vias. And so a via, like so, is just a chunk of tungsten, which I believe I've mentioned before. Each via has to be 2 lambda by 2 lambda. These are the restrictions from the SC-MOS design rules. And each via has some resistance. Ten ohms per. So the resistance to this via of 10 ohms is actually significantly larger than the resistance of the metal layers. So if we put a single via in, we would see that there would be significant ohmic losses over the vias that could potentially cause a phenomenon like ground bounce and things like that, which we really wouldn't want to do. So instead of placing a single via, which generally speaking, is a bad idea to begin with, because if that one via fails, then you no longer have a conductive path between the two metal layers. We'll put multiple vias in parallel. And typically speaking, you want to cram in as many as you possibly can. In this drawing right here, we're going to put in 10. Well, what's the effect of putting 10 vias in? So here is our metal 3 node. Down here is our metal 2 node. And we have between those nodes 10 vias electrically connected in parallel. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for this particular case, instead of having 10 ohms of resistance, we have, let's see, so 10 in parallel. So 10 ohm resistors in parallel should look like, I believe, 1 ohm. So we've significantly lowered the contact losses between the two metal plates, which is good. We have now multiple points of interconnection between the two metal layers, meaning that if one fails, we're still able to pass a signal from metal 3 to metal 2 and vice versa. And yeah, so that's why we're going to try to use as many metal layers as possible whenever we get into the design process here. And one way to allow that to happen is something that we talked about in last class, where we use very wide wires, which will lower the overall resistance of our wires because we'll have less squares to account for. And that also enables us to put multiple vias in to lower the contact resistance between the metal layers. Okay, so I believe the last couple of topics that we're going to discuss with regard to the metal layers are some of the kind of negative effects that we need to be on the lookout for. So, the first limitation that I want to talk about is current carrying limitations of metal layers. A conductor carrying too much current causes what we'll call metal electromigration. Now on the macro scale, what happens when we have a wire that carries too much current? Anybody have any idea?
It heats up.
So to be clear, I have a class full of electrical engineering students and graduate students, and none of you knows what happens when you pass too much current through a wire.
Sorry, he spoke up before I was going to. I mean, it'll melt or disintegrate essentially.
It's turned down. Oops.
Can you hear us?
I'm not sure if he can hear us.
I know he said something about having to turn up the volume.
Okay. Sorry, my volume was turned all the way down, so I couldn't hear anybody answering. I apologize for that.
Grant and Alexander said that it'll melt or disintegrate your wire.
Exactly right. So the wire is going to melt, and we should see roughly the same thing happen on the micro scale. We just give it kind of a fancy name. So electromigration is a process or phenomenon where the metal layer physically moves or deforms. Okay. So what's going to happen when we get that deformation is we can see that our wires can actually kind of, I don't want to say they become like a liquid or anything like that, but they physically become wider and potentially thinner, which causes a change in the overall sheet resistance. So we can see some very adverse behaviors if we pass too much current through a wire. So to avoid that, we have to keep in mind what's called the metal migration threshold current density. Which for aluminum, the metal used in most CMOS processes for creating wires, is roughly 1 milliamp per micron. So let's say that we have a metal wire that is 3 lambda wide and a bonding pad that is 72 micron by 72 micron in a C5 process. That is 300 meters. What's the maximum current both of these conductors can carry? So for the wire, it's fairly straightforward. Maximum current is simply the metal migration threshold current density times the width of the wire, right? So the length of the wire doesn't contribute. If we have a long section of wire, current is going in this direction. And so we're looking at this direction as to what contributes to the overall current flowing through. Right. So 1 milliamp per micron times 3 times 300 times 10 to the minus 3 microns for 300 nanometers. Gives us a current of 3 times 0.3 is 0.9, so 0.9 milliamps, or 900 microamps. So a reasonably decent amount of current can pass through a 3 lambda wire, at least in our C5 process, using aluminum as our metals. But if we wanted to say make a 20 amp current or 20 milliamp current mirror or something like that to be able to feed things, we're going to have to realize then that we need to make our wires much, much longer to handle even that small amount of current. For our pad, we're going to have J aluminum times the width of our pad, which in this case is 72 microns. So 1 milliamp per micron times 72 microns is 72 milliamps. So the levels of current that we're going to be able to pass into and off of the chip are going to be fairly small. So in order to design, say, a high power operational amplifier, we would have to have significantly larger bonding pads and all that kind of stuff. Now, one of the limitations, I guess, that we'll be working with is we're going to be using fairly small bonding pads because the way, well, so let's talk about this a little bit. We're not going to be able to send our chips off to Moses because the lead time right now due to the coronavirus is absolutely ridiculous, like somewhere on the order of a year to 18 months. Originally, like what I had the students do last year, everything was designed in such a way that we had, I think it was close to 40 pins on our chip that we designed, where we had, I think, 4 pins per student effectively. So we put everybody's thing on a single chip. We can lift those kind of restrictions this year just because we're not going to be able to send anything off to actually get fabricated. Okay. Where did I put my thing? All right, so the last thing that I want to talk about today with regards to metal layers is crosstalk. So let's say that we have, again, just using metal 3 for the sake of argument, we have 2 parallel conductors. So that would be a top view, and then we can kind of look at a side view as well. So let's say that we had our substrate. A little bit of insulation layer, which I don't think I changed the color there like I was supposed to. And that insulation will be all of the different insulations that we need until we reach our metal 3 layers, where we would have something that looks like this. And these aren't floating off the top of the substrate. I'm just trying to give it a third dimension so that you can kind of see what's going on here. So we have those metal wires laying on top of the substrate. They are going to form a capacitance, and the capacitance that they form is dependent largely on the spacing between the 2 of them. So a signal voltage propagating on one of the conductors may couple current onto the opposite conductor. We'll call this current IM, where IM is the capacitance value times the derivative of the voltage passing through conductor A. Let's call it the one on the left, it doesn't particularly matter, with respect to time. So the current through the capacitor is C times the derivative of the voltage. So C dV by dt. This should not be news to hopefully any of you guys at this point, because that's the basic relationship for current and voltage in a capacitor. And just to make sure everybody's on the same page, where Cm is the mutual capacitance and VA is the signal voltage on the source conductor. To determine Cm, an experiment is applied carried out where a step voltage is applied to one conductor and a coupled voltage delta V, or V delta, I think in the textbook, is measured. Since we know the capacitance of any conductor to the substrate, we can find that delta V, or yeah, now I have it as well. Let me go back to V delta so at least I'm consistent. Is our applied voltage times Cm over Cm plus C sub, where C sub is the capacitance of the adjacent conductor to the substrate. The adjacent metal line also exhibit a mutual inductance. where the two nearby wires form a mini transformer. The current flowing in one conductor induces a voltage in the other. That is a terrible looking V. Oops. And we measure this by determining, or excuse me, injecting current into the system, into one conductor, and then measuring the voltage drop that occurs over the other. So we can see that because these conductors exhibit both a mutual capacitance and a mutual inductance, we have to be very, very careful about the physical spacing between two nearby conductors having different electric potentials. If they have the same electric potential, then there's no voltage drop, or there's no voltage difference between them, which means if there's no voltage difference between them, there's no charge difference between them, so the capacitance is effectively, the mutual capacitance is negligible, and we won't see this coupling. So that's part of the reason why the design rules say there can, the spacing between metal conductors of different potentials has to be a particular value, but the more space that you can put between your conductors, the smaller amount of problems you're going to have with crosstalk and effectively signals, bouncing around inside your system and making things behave like they are not supposed to. All right, so let's take about a 5-minute break, and then when we come back, we're going to talk about, let me check my notes here. I believe we're going to talk about the active layers, and perhaps if we have time today, the polysilicon layer. So at roughly 8:48, we'll meet back. Alrighty. Save this. Alrighty, so we're now into chapter 4, which is about the active, select, and polysilicon layers and what we can do with those. Is really the last few layers that we haven't talked about in our C5 process. The first thing that I'd like to talk about is the active layer. So in previous talks, we had, talked about N wells, P wells, and stuff like that, but we never really talked about how they were made specifically. And I think I also talked about implants and things like that too. So what the active layer is it's the layer that defines holes, like physical holes, in the field oxide layer. And it also enables access to the substrate. So a top-down view would be something like this. And this layer goes hand in hand with another layer that we're going to be talking about today. So this is our active layer. And then surrounding the active layer, we're going to have what's called a select layer. Call this guy P select for the sake of argument. And so what we would see in our cross-sectional view of this situation, here would be the top of our substrate. Here would be the bottom. This is our field oxide layer. And so the active region, or the active layer, is what tells us to effectively etch a hole specifically in the field oxide layer of that particular shape. And then the P select layer is what tells us to put in P-typed dopants, so that we would have, let's say for the sake of argument, that this is a P plus implant, but it could just as easily be a P well. And I've drawn it specifically with square sidewalls like this because of what we're going to talk about in just a moment, okay? So after the annealing process and all that kind of stuff where diffusion occurs, we would actually expect it to have curved sidewalls like so and extend underneath the field oxide layer a little bit, which is how my previous drawings have looked. But I guess just let's get to it. So the P-select layer, or the select layer in general, needs to overlap the active layer to eliminate positioning errors in the implant due to mask misalignment. And so what that means, like let's say that you were trying to put in the implants for a transistor, right? So you actually shine the ion beam, or not the ion beam, but the dopant beam over an area larger than it needs to be, because if you bury a few excess charge carriers inside this highly insulating field oxide layer, it's not going to turn it to be conductive. But if you were to shine it directly on just the area that you thought you needed, and the masks were misaligned and things like that, you could have regions like I'll draw another one over here. So if you had misalignment, your field oxide layer, something like this, and something like this, your select prior to diffusion might look something like this, right? To where you have this region from here to here, where you were supposed to have effectively a highly conductive material, and you do not. And so not having that highly conductive material in that space could lead to your transistor or something like that effectively never being able to turn on, which means that your device could potentially fail unless you have lots and lots of redundancies in place, which is a common practice nowadays. So we need the select layer to be larger than the active layer so that we're sure to irradiate and implant dopants into that whole region that's exposed by the opening in the field oxide layer. All right, so the active and select layers may be combined. In some layout editors. So I think, gosh, what's the one that's made by OrCAD? Cadence. I think it's a single layer, but electric, it's 2 layers. All right, and to be clear here, because we're going to be using the active and select layers to define both wells and implants, it may be important to know the difference between the two. So the difference between an NP implant and an NP well is largely their resistance. So it's really a function of doping concentration, but the observable effect is that we saw previously the resistance for a well somewhere on the order, at least for an N well, 800 ohms per square, and the resistance for an implant is somewhere on the order of 100 ohms per square. Typically speaking, N plus is around 100 and P plus is a little bit higher at about 125, but these values will vary with the process, and they will also vary with every single fabrication run as well. All right, so that's the active layer and the select layer, and we'll, let's see. Yeah, let's talk about this next. So connecting to the substrate, or specifically grounding the substrate, okay? So multiple times at this point, I believe I've mentioned that the substrate, the P-type substrate in a CMOS process is typically at ground potential. Now that is important due to the body effects in transistors that we'll talk about in a couple of days and all that kind of stuff. But how it's done is also important, because the substrate isn't just inherently at a potential of 0 volts. We actually have to apply, we have to connect it to an external ground to the chip to cause that to happen. So let's see. How we might go about doing this is we would define, I think this is the color I used. An active region. Like so. So this is cutting a hole in the field oxide layer. We would then put in an implant. So we would have specifically a P-select layer. We want to put in a P-type implant. And the reason why we need to put in a P-type implant specifically is because our substrate is also P-typed dope. So if we put in an N implant, we would be forming a PN junction, which would mean we'd be making a diode, which is not remotely what we want, because we want, we're trying to ground the substrate, so current needs to flow into or out of. We don't need a one-way valve on the current. We need it to be specifically P-type. So this is our P select region. And so let me draw with this simultaneously what's going on the cross-sectional view. That's the wrong color. So let's see. Here's our field oxide layer, and let's cut it off there. This is 5 wide, right? Yeah. So that's our field oxide layer. We put in our P select, which is going to give us a P plus implant. Down here is our P substrate. The next thing we would do is define where our vias are going to go. So in this case, let's do 6 for the sake of argument. So we would put in our tungsten plugs. Throw our oxide layer again to fill in those gaps. And then we would put in our metal 1 layer. And so we'll have that oxide with holes in the oxide, and here is our metal 1 layer. And then from there, we would have to go through metal 2 and then through metal 3 to get to a bonding pad or whatever to connect externally to ground. So this is roughly how the process of grounding the substrate goes. Now notice that we have P plus here, so this is doped P-type, and this area is also doped P-type. There is a difference in concentration levels, but it's P-type semiconductor connected to P-type semiconductor, and that is extraordinarily important. Again, we won't form a PN junction, and we're not trying to apply metal directly to our substrate, which would give us a Schottky diode. So we have to connect a P plus implant to our P plus substrate in order to have what's called an ohmic contact. And the ohmic contact is the type of contact where we don't wind up accidentally creating a diode. All right, so I explained things there. Now let's talk about our polysilicon layers. And the polysilicon layers are going to be very important to transistor fabrication, as well as a couple of other things. And we'll talk about them more when we're dealing with chapter 5, which is dealing with specific components in an integrated circuit for a CMOS process. All right, so this is our last topic for the day. Polysilicon layers. So as the name implies, the polysilicon layers are formed with chunks of crystalline silicon. So our substrate is a single crystal silicon wafer where the grain is all in one direction and all that kind of good stuff. Polysilicon layer is we have chunks of crystalline silicon that are heated up and then deposited onto usually on top of an oxide layer or something like that. Since the grain structure is very, very different than single crystal silicon, we expect to see that the resistance is significantly different and other material properties are different as well. So excuse me, the information I have in my notes right here says that the resistance of the poly 1 layer is approximately 25 ohms per square. But that's not entirely true. And so let me explain what I mean by that. So the resistance of the poly 1 layer, which is the layer that would form the gate of a transistor, it's only it only has that resistance because the gate itself is exposed. So the polysilicon itself is exposed when you are doing the ion or the dopant implantation. So raw polysilicon crystalline actually has a significantly worse resistance than single crystal silicon, but because it's doped at the same levels as what the source and the drain of the transistor are going to be, that's what makes it electrically conductive and brings the resistance level down to this value. Okay, and we'll talk about that when we talk about self-aligned gates, which I think we'll cover on Thursday. Alrighty. So we can use the poly 1 layer to make small 50 to 500 ohm resistors, right? If it's only got a sheet resistance of 25 ohms per square, we can't use it to make large resistors because we'd have to use an awful lot of it. But to make small value resistors, this is a fairly reasonable way to do it. But it's mainly used to form the gates of Mosfets. That doesn't look very good. The poly 1 layer is physically directly above the gate oxide for a transistor. And the poly 2 layer is above poly 1, which I think we've discussed earlier. Not all processes have 2 polysilicon layers, but the one that we are working with does. So we'll talk about it. The poly 2 layer can also have an additional layer put on it, and additional, which blocks dopant implantation to keep the material at a high resistance. Roughly, and we're going to call this HZ, high impedance really, but it's resistance, DC resistance, at approximately 1 kilo ohm per square. This is the, I don't want to say best way to make large value resistors, but it's definitely a good way to make large value resistors. And the reason for this is, if we notice the sheet resistance of the high res poly layer, let me just put in here, high res poly, because that's what it's called usually, is only marginally larger than the resistance of an N-well resistor, right? So we're talking about a difference of 200 ohms per square, not a whole heck of a lot in the grand scheme of things. But a poly 2 resistor is not placed into the substrate, okay? It's actually sitting on top of the well, it's sitting on top of an insulating layer, which is sitting on top of the substrate. So for an N-well resistor, if we change the potential applied to the N-well resistor, we are also changing the dimensions of the space charge layer, or the PN junction formed between the N-well resistor and the substrate, right? So if we're changing the size of the depletion region, every time we apply a different potential to the resistor, we're also observing that it's going to have different RC characteristics. It's going to potentially change the sheet resistance a little bit as well, because the thickness of the well, there's going to be an area of it where there are no free charge carriers if we make the depletion layer larger, or it's going to have more free charge carriers if we make the depletion region smaller. So the overall behavior of the resistor is significantly more constant in a high-res poly resistor. So that's probably the largest reason why, even though we could make everything using N-well resistors, why using a high-res poly resistor makes the most amount of sense, especially in analog design, where the actual value of resistors is critically important. In digital designs, the value of the resistor itself, usually not so big of a deal, but when we're trying to make an operational amplifier where we're going to have to do specific feedback configurations and all this kind of stuff, and size resistors very specifically so that our bias points give us the most amount of headroom, having a precision resistor is going to make the most sense. All right, so we're finishing up today about half an hour early. On Thursday, we'll talk about, we'll cover chapter 5, which chapter 5, let me look at the title of it real quick. Let's see. So chapter 5 is called Resistors, Capacitors, and Mosfets. Now, you may think that we have beaten resistors and capacitors to death in this class because we've talked about them a bit here in the high-res resistor, or in this lecture. In our first lecture with N-wells, we talked about resistors, but we're going to talk in a more general sense about the implementation of resistors, how to match them, and things like that. So it isn't going to be just full-on review over resistor and capacitors. We're going to talk about some more specific concerns with the placement of resistors and capacitors than we did when we were talking about the specific concerns with the particular layers that we use to implement them. So it is a little bit more of the same, but it's also from a slightly different perspective. So hopefully you guys won't be wildly bored with it. Then we're actually going to get to start talking about transistors and all that kind of good stuff as well, and some schemes on how to minimize their footprint while achieving the particular width-length ratios that we need, because hopefully all of you guys remember from your analog electronics classes that, you know, say the drain current is directly proportional to the ratio of the width divided by the length in a transistor, but sometimes we can't have, we don't have the physical footprint necessary, so we can do things like fold them or other things like that to help us put in resistors that'll give us the specific characteristics we're looking for. Okay, so that's enough out of me for today. So I'll see you guys on Thursday.
Have a good one.